Hi, and welcome to day 6 of Keysight University Live. I'm Daniel Bogdanoff, a test gear geek here at Keysight, and we are live in Colorado Springs. We're now in the weekly phase of this event. We'll have a new video, interview, and prize drawing each and every Tuesday until the end of April, so make sure to mark your calendars. If you check the web page, we have a few things happening each day. Right at the top of the page is the stream that you see now. We also have some chat on the side. This is live at 10 a.m. Mountain Time each day. We have some information down below that video. We'll also sometimes put some links there if I promise a link during the stream. We, at the bottom of the page, also have a daily video that's a little more polished. We also publish these on our YouTube channel, but you can see both videos here live at the same time. So check it out here. It's probably the best place for it because you get it all in one place. In addition, on this page below the chat are 2 buttons. There's a Get My Daily Entry button. You don't have to press this button, but it does get you an extra entry each day. You can get 1 extra entry each day. Even if you refresh the page and keep hitting the button, you're going to get max 1 entry for that day. And there's also a sign up for exclusive access, send me special emails sort of a button there. Basically, we are planning some great things after this event is over just for people who participated in Keysight University Live. So make sure you click that button so you get those updates. If you don't click that button, there's a good chance we cannot send you that email or keep you updated and informed. So make sure to hit that button. And at the bottom of the page, we have a couple more things going on. First, there is a link to see both the schedule of events, which has all the different days and what's going on each day with links to each of those days. Or you can scroll through different days using the link at the bottom. So today's day 6. There's a link for day 5. You can go see what happened on Friday. And at the bottom of the page, we have a featured Keysight University Live course. Today is with Matt Ozales, and we are actually interviewing him later, but we'll talk about that more in a moment. And the Smart Bench Essentials Challenge. So if you don't want to leave your test gear up to chance, you can also enter the Smart Bench Essentials Challenge. And we will announce the first winner of that event, of that challenge at the end of the stream when we announce the rest of the winners for today's drawing. And if you want to see our new Smart Bench Essentials products, you can go check out that catalog there as well. So real quick, you can see other days by clicking day 5, and you can see what happened on Friday. We tested a cheap Amazon charger, so go check that out. So that's what's going on the page. The page is basically the same each day, but we update it with the different videos. Today's interview is awesome. We are with Matt Ozales, and I learned a lot from this interview, including things like 3D Smith charts. And he's actually helping out with the chat today. So if you're here live, you will see this video in the webpage. And if you have questions or comments, both Matt and the team will be responding to those chats. So you can actually talk to Matt in the chat. If you're not here live, we start all our streams at 10 a.m. Mountain Time. So make sure to set a reminder in your phone so you can turn in. And you can also watch the replays, but then the chat goes away. So we'd love to see people here live. We've had a blast. We'll also do some Q&A at the end of this video. So if you put questions in chat now, the team is monitoring those, and I will take those at the end. In that video at the bottom of the page, I drove this car with a function generator through an obstacle course. And since those function generators, we thought for today, we would quickly have a video about the function generators that we make. So let's take a quick look at that, and then we'll jump into the interview. Hi, I'm Daniel Bogdanoff from Keysight, and today we're going to take a quick look at the 33500B and 33600A series function generators. They come with exclusive TrueForm technology that offers more capability, signal fidelity, and flexibility than previous generation DDS waveform generators. Function generators are an essential bench tool that provides stimulus to a device under test. You can then evaluate how your device performs by inputting a known good signal and monitoring the output. These TrueForm function generators have a variety of capabilities that you can't find anywhere else. Capabilities designed to help you accelerate your testing and get your projects completed faster. They are extremely easy to use. As you'd expect, TrueForm function generators offer the standard signals and features like modulation, sweep, burst, and signal summing. They also have a large color graphical display that lets you set multiple parameters simultaneously and gives you quick viewing and editing of your signal. There's a front panel USB port for file management and a built-in help system. We call them TrueForm generators because of their industry-leading signal integrity. That means you get clean, precise, low-noise signals for testing. You can generate the exact waveforms you need for your most challenging requirements. You can be confident you are seeing your design's characteristics and not worry about measuring artifacts from your waveform generator. TrueForm offers precise, low-noise signals with the lowest jitter at less than 1 picosecond and lowest harmonic distortion in its class, 0.03% total harmonic distortion. TrueForm ARBs ensure every waveform point is accurately represented with up to 64 megasamples per channel. TrueForm generators use a technology that plays every point in your signal exactly as you designed it. That means when you're testing the robustness of your design, you can create a specific signal with noise, overshoots, spikes, and dropouts precisely where you want them. You can segment waveforms to simplify waveform creation, and to save memory, you can sequence and loop up to 512 waveform segments. TrueForm function generators also allow you to create a single pulse, a burst of pulses, or a steady pulse train with high bandwidth, up to 100 MHz. Most DDS-based generators offer reduced bandwidth when generating pulses. TrueForm function generators produce higher harmonic content, allowing for rapid transitions. Like a dedicated pulse generator, edge times can be set independently down to 2.9 nanoseconds, which is twice as fast as a typical function generator. Channel coupling simplifies the operation of a two-channel function generator. Both channels can be controlled with a single parameter for phase, amplitude, or frequency, making it simple to create differential or tracking signals. The phase between the channels is also adjustable. You can connect and control your function generator over LAN, GPIB, USB, or even a USB thumb drive. The BenchView function generator control and automation app makes it simple to connect, control instruments, and automate test sequences so you can quickly move past the test development phase and access your results faster. It only takes a few clicks. With BenchView, simply point and click to control your function generators. You can also get advanced waveform creation and editing capabilities with the embedded Keysight BenchLink Waveform Builder Pro. You can rapidly build custom test sequences with TestFlow and access deeper instrument controls with Command Expert integration. The 33500B and 33600A series function generators are also upgradable. There are 4 different models to choose from. You can purchase the capability you need now and simply upgrade capabilities later to match your changing project needs. Your investment in this test equipment is protected. For example, if you need deeper memory for generating more complex signals, you can easily add that capability later with a software upgrade. And there's no price penalty for adding the capability later. For configuration questions or a demo, contact your local Keysight representative at www.keysight.com/find/contact us, and you can find more information and model-specific specs in the datasheet. Thanks for watching. So these function generators are insanely powerful, and we actually use the same chipset in the new SmartBench Essentials function generator, so there's a lot of shared technology between the two. So check those out in the SmartBench catalog at the bottom of the page if you want to learn more about what you can do with these. We've also done a couple videos with function generators, so you can go searching through both our blogs at blogs.keysight.com and our YouTube channel, Keysight Labs, the Keysight Labs channel on YouTube, and you'll find some information about that. Today's interview is with Matt Ozales about RF simulation. This is something I knew very, very little about, so I was really excited to sit down with Matt, who's one of the leading experts in the field, to learn more about this. So why don't we just jump straight into that interview, and we'll jump in with Matt. Remember, Matt is in the chat, so if you have questions, put them in chat, and we'll be watching them. I'm joined today by Matt Ozales. He worked for over 10 years doing high-frequency amplifier design and cellular communication RF magic stuff. And recently he came over to Keysight and has been working as, I think his technical term is application developer and scientist. Thank you so much, Matt, for being here.
Thanks for having me. It's great to be here.
As my intro might have implied, scientist is a new title, and maybe you think of yourself more as an engineer, but you find yourself in this hybrid role doing simulation work. So why do we even need simulation, and why can't I just test everything on the board once it's done?
Yeah, I mean, it used to be that you could. In fact, I remember when I first started working, simulation was like something you did on the side, and I remember thinking it never works. Simulation would always you could simulate a filter and tweak things around and stuff, but you'd never get it exactly right. You always had to go in the lab and kind of fix everything. There's a couple things that have happened since in the last 15, 20 years since then. The first is that the compute power has really increased so much. So all of a sudden, electromagnetic simulations that we could have never dreamed of doing just a few years back, all of a sudden with the compute power we have, we can do these electromagnetic simulations really quickly. We can parallelize them and get results. So that's one key, that enabler to give us the accuracy. The second is just the simulation technology, the algorithms, and the ability to combine like multi-physics stuff, electrothermal, electromagnetic effects, circuit, nonlinear circuit simulation. Combining all those things together, that technology has really improved in the last couple of years. And so the first piece, I guess I would say, is the simulation has become accurate enough to be able to match measurements. So to the point where you can, if you know what you're doing, you can simulate something and have it work the first time. The second piece is, and we see this in actually some of our equipment. Like if you start, you look inside some of our Keysight boxes, our scopes, Infinium scopes, you'll start to see that our older packages are like these hybrid types of packages where you've got chips and you've got wire bonds and you have all these little thin film pieces to them. And if you're in the lab, you can go in and kind of rip those apart if you know what you're doing. If you have a good technician, you can do a lot with that. What we're seeing for cost reasons and also just for performance, you can sort of keep the electromagnetic signals more closely tied into your part. People are moving to these crazy advanced packaging technologies. So things like fan-out wafer-level packaging. And what that means is you can't go in there with a soldering iron and a scalpel anymore. The package is completely contained. There's nothing you can do. So a lot of times you just can't access the nodes that you would need to go and fix problems like that in the lab. So you have to get things right up front with the simulation, or else you'll never be able to fix it.
So how often do things go wrong? So everything was simulated, it comes out clean 90% of the time, or where are people having where's the gap now between simulation and reality?
Well, I think a lot of the gap is more in understanding and the ability to apply techniques, right? So one thing we're seeing, like with stability analysis, one of the things that we're seeing is there's really this move to higher frequency transistors, and higher frequency transistors really change the game as well. So to get gain at like 30 or 60 or 90 gigahertz, whatever, you need a ton of gain at lower frequencies, and that gain causes all kinds of stability problems at lower frequencies. So it's partially the techniques and just the ability to combine the different tools together. It used to be like when I was designing, I would use a technique called K-factor. I'm sure most high frequency designers have heard of that technique. But it turns out with the types of circuits we're using today, it's just not sufficient to capture those types of problems. So you need to kind of change techniques and be able to use different things. With the modeling, it's all about. I tell people it's all about modeling what's important. So there's some things that you can if you don't model it, it doesn't change anything. It doesn't change your results. And if you there's other things that if you just tweak a little piece of coupling between two different vias on your chip or something, and all of a sudden your results will shift dramatically. So a lot of what we do in simulation is just trying to figure out what's sensitive in our circuits. And the things that are sensitive are the things that are important to model.
And that makes sense. I suppose if you take that to the extreme, you don't need to model like the sun rising in the east to make your chip work.
Or every electron.
But you do need to model ideas.
Yeah, I mean, you could. I mean, that's true. We could go model that, and we abstract things to certain levels. And I tell people, you don't want to model everything. Actually, only model the things that are important. And there's a few really good techniques. Actually, simulation and measurement. There's so many different, so many similarities between these two areas. But one thing we can do in simulation is actually apply a measurement technique that people have been using for many years on wafers called design of experiments. So people have been using this to figure out sensitivities on like chip wafer designs. And what it does is you essentially vary a parameter, and you can figure out by varying sets of parameters which combinations of things are sensitive. Like, do you have a cross correlation if for example, in your process, this capacitance value is low and this inductance value over here is high in some corner case? That may have an impact on the performance of your circuit. That means that you need to really pay attention to modeling those things in your design process. So, and that we see that with a lot of cases. Measurement techniques, simulation techniques can kind of come together.
It sounds very much like, I'm going to say the real world, but like outside of the matrix, where you're tweaking trimmer potentiometers and kind of just poking around to see what happens, but now you can do it in software without having to like refab a chip or something like that.
Yeah, I mean that's the hardest part. A lot of times, the design cycle for chips and refabbing a chip or whatever is going to take months out of your design cycle, and so yeah, you want to get as much right the first time as you possibly can. And it's amazing, people are making these crazy complex products and they're turning them on and they're basically working. Like I've seen stuff where in some of these new phones, and you think they couldn't possibly get this to work on the first iteration, but with the simulation tools, you can put it together to the point where we're not fixing problems like the gain isn't right. The gain will be perfect. The compression characteristic, efficiency, that stuff will all be perfect. And now the engineers are into these second and third order effects that they're solving in the lab. So it lets you get such a running start by knowing how to do that.
How much can be simulated? How much analysis can you do of a circuit? Is it pretty narrow focus, or is it like plug in Maxwell's equations and run free?
Well, I mean, there's always a trade-off when it comes to the simulation process. It's always like this speed, accuracy kind of trade-off. So you can get you can simplify things. Imagine just a filter or something. You could just take a bunch of lumped inductors and capacitors, and that'll simulate really quickly. But when you lay it out on a board or something, you're going to have spirals. You're going to have all these electromagnetic effects, and it's going to take a little bit longer, but you'll get a more accurate result. So I look at it as almost a knob between the accuracy and the speed of the and it just depends how complex your models are. So yeah, I mean we can definitely model one of the most interesting things that I've seen is the electrothermal effect. So for example, on a transistor, when it turns on, of course it gets hot, and we can model those effects, and those thermal effects have an electrical effect on your circuit. And so one of the things that happens is memory. Well, so the transistor will heat up, and there's a lag. The area around the transistor takes time to heat up. It's like a big capacitor. And so those things can actually affect the electrical performance of your circuit. If the transistor's not as hot as it should be, then it's there's going to be like a spike or a blip if you give it a pulse. So yeah, there's all kinds of effects we can model. It's pretty amazing.
So when it comes down to the rubber meeting the road, or the silicon meeting the fab, I guess, what are people really trying to walk away with? A design verification? Is it simulation used as a tool to get to a final design? What's that like end goal for folks?
Yeah, I mean, the end goal is to get to a design that is going to essentially work out of the box the way you want it. So the first, of course, there's a cycle that takes place. That you do the first rev, and you're trying to get something that's workable. In some areas, depending on who you talk to, that means like getting a sample out into a product. So if you have, just a simple one, a cell phone, right? If you're making the first spin of that, you just want to get a part into a phone so that it's generally working. It's not like violating all of the the FCC rules or whatever. And then from there, you're really just tweaking small areas of performance. So you get into these really complex problems, and that's where the later revs of simulation, as your modeling evolves, then you start talking about things like getting the yield to be better, higher yield, figuring out what areas in your design are contributing to those places of low stability problems, like we were mentioning, solving some really hard to understand issue. So you can go in then and really target a particular problem that you're going after, and really focusing on on modeling that one effect.
Okay, so it's again pretty open ended in terms of what you can achieve with it.
Yeah, I've seen people go in and try, and they're making millions of parts, and they can get the yield, right. I've also seen people combining, scenarios where they're doing beam steering now, and they're able to go from like they can connect a chip to an electromagnetic structure and then change voltages and currents down in these little transistors, and you can see the far field radiation pattern out in the space. To be able to model that in simulation. And if you think about it on the measurement side, that's a tough measurement to make. It's of course possible, but you need like an anechoic chamber and all that stuff. So being able to do that in the simulation tools can be pretty helpful, especially if you can get accuracy in it.
Yeah, I was just looking at a beamforming antenna that, like, for testing your millimeter wave arrays, and it was like a $40,000 antenna just to be able to test the physical parameter of one beam steering chip.
Yeah, it's good to be able to test that. And the other thing is, especially like if you don't want anybody to call you, the best thing to do is just go into the anechoic chamber, and then nobody's going to be able to reach you on your cell phone. So you don't get any Wi-Fi signal. You can have peace and quiet.
So the upside, the upside of doing it all in hardware is you get to hide out from your email inbox.
That's right. Yeah, you close the door, the screen room, and it's really quiet.
Okay, so understanding fundamentals seems like a pretty big deal. And one thing that came up as we were talking earlier is three-dimensional Smith charts. So can you start with how important is it to understand the Smith chart, and then why the Smith chart maybe isn't enough when it's flat on a piece of paper or a screen?
Yeah, well, I mean, the Smith chart is, of course, one of the most important things, and a lot of people, I mean, when you look at it in the older days, I remember, like, I don't know if people even still do this anymore, but you have a compass, a compass, and then you would make the circles on the Smith chart and everything, and trace things out on a printout Smith chart. And I hope I don't know if students still do that today, but understanding that transformation between like the impedances and the reflection coefficient, that's everything in our field. So that one graph that was made, however many years ago, is still so important and so powerful to communicate the way that these types of high frequency circuits work. So I've had people say, well, if you understand the Smith chart, then being able to design hardware in the lab or with software is going to be really easy. But if you don't understand the Smith chart, you're not going to be able to go in the lab and make a high frequency circuit work, and you won't be able to get the software to work for you either. If you don't know how that works. Yeah, the 3D Smith chart is also called the Smith tube. And by the way, I didn't invent this. It was actually invented by a fellow named Dr. Charles Bayliss, and there's a team in Baylor University who put this out. I think it was in like 2014. And I just read the paper and I thought it was really cool. I thought it was one of the most interesting things I've seen in a long time. So I implemented it using one of the things we've been trying to do with the software tools is connect them into more like programming languages. So one of the things we use is Python. And so I connected it in, and I built a little Python module to make this Smith tube. And that's what you can really do. And I can provide a video, but you can take like an S parameter response across frequency. Say you have a matching network. Well, all of your little inductors and capacitors, like you have a series inductor, shunt capacitor, those are going to shift your impedances on the Smith chart. And you can look at those at one frequency and see how that works. It gets you to a point. But when you're sweeping frequency, there's a lot of different, points of inductors and capacitors. They're all moving a little differently. So when you can stretch that out into three-dimensional space, all of a sudden you can start to understand how your components are shifting your matching network across frequency, and you can get some really interesting effects. So this one simple matching network I was looking at a resonance, and you can see how if you spread it out into 3D, you can see how one of the capacitors is actually kind of spinning around an inductor, and it creates this like helical shape on your three-dimensional Smith chart, which is actually a resonance. So if you're trying to design that resonance and you're making the matching network, you can figure out exactly what's going on in the matching network, which component you might need to change to shift the frequency of that resonance. So
I suppose you could also use that to figure out what frequencies to avoid and have avoid resonance you don't want in a system.
Yeah, exactly. Yeah, avoid frequencies. In fact, one other area that I thought was an interesting application is a lot of times you see people plot contours on the Smith chart. So contours are just concentric circles, and I do a lot of hiking, and I use some elevation books. So when you're looking at these contours, you realize, oh, that's just cartography. This is just a three-dimensional structure that's flattened down to a two-dimensional structure, just like lines of elevation on a map. And so what I started doing was plotting these three-dimensional structures onto this Smith tube, this stretched out Smith chart. And you can find, all these really interesting pieces to it. One of them was error vector magnitude. I had an amplifier. I was trying to optimize it for error vector magnitude. And I had these contours, and they were just a weird shape. And when I plotted it out, the entire, curve, the 3D surface, it turned out to be this like narrow valley, and you're trying to put the impedance into a Smith chart. But if you moved just a little bit away from the area where, you got the best EVM performance, there was this really sharp peak. It was like a really, steep slope peak. And so you need to avoid that area. Well, if you're just looking at the contours, you're not necessarily going to see that steep peak coming out of it. So yeah, it's really helpful to be able to look at entire sets of curves and surfaces on a Smith chart. So
I'll have to go check it out. Seems interesting.
Yeah, you should. Yeah, it's definitely it's a lot of fun. It's certainly entertaining. So, and you can make some really good plots out of it. So it looks really complicated, which is.
So that's one where we used to do that with XY mode on our oscilloscopes, as we pull it up and have it like doing crazy stuff just to look like we were doing something really complicated.
That's right.
Like a function generator plugging in. So So who is moving into the simulation space as far as what engineering disciplines are starting to realize they need it, and what are they struggling with as they move from physical testing into simulation?
Well, I think a lot of it has to. One of the things we're really seeing now is just a migration, and I don't know if it's just on the simulation side, but we're finding engineers who used to just be sort of analog designers, relatively low frequency. They might design like op amps and some of those types of circuits. All of a sudden, they're now being asked to design circuits in the gigahertz region. So we're seeing a big shift of people who are used to these analog types of designs moving up to maybe even millimeter wave frequencies, and sort of realizing that this is a completely different ball game at these frequencies, that every little interconnection matters, and it propagates your signal through. It's no longer just a switch anymore. It's a wave propagation. And one of the things that's most apparent on is for example some of these digital systems. So you have really fast signal that switching signals with clocks, and those signals are starting to become a lot more like microwave signals. And so digital designers are now having to move, migrate into this microwave region and try to understand. So, if you're doing these digital lines now, you have to start running electromagnetic simulations to see the effects on your lines. So I'm not sure, it's like entirely new people coming in. I think it's just people who are in different disciplines are now starting to have to deal with higher frequencies, and that's one of the biggest things we see.
That makes sense. Do you have any fun horror stories of, oh, we should have caught that, or we caught this before it went into production?
I always have horror stories.
Obviously not like. Obviously,
well,
don't call
one of
it company names, but.
Well, there's all kinds. When it comes to, certainly oscillations would and instability in circuit design would keep you up at night, because when you're designing these types of circuits, I think one thing a lot of people don't realize is like you can have a perfectly stable circuit in a 50 ohm system, but then if you stick an antenna on that, the antenna. Okay, so let's say you're designing it at 1 gigahertz. Well, the antenna is tuned for 1 gigahertz, so you're good. You don't have to worry about that, right? Until you start thinking about the other frequencies, and like you start asking, well, what does the antenna do at 100 megahertz or 50 megahertz, and you realize it's really reflective. And so that leads to this idea that with a lot of amplifiers, you actually have to run load pull, and you start to try to characterize your amplifier and make it stable over all of these load conditions. So 10 to 1, 15 to 1 viswars, you're going to start pulling and seeing if your circuit is still stable under those conditions. And I got to tell you, that is a nightmare. It's a nightmare for a lot of our customers, because you have this thing stable at 50 ohm condition. You start pulling a 10 to 1 viswar, and then you get this Christmas tree effect where the spectrum completely, all these things, all these issues pop up in the spectrum. And it's like that old game of whack-a-mole. Like when I was a kid, you'd go to the arcade and you try to hit the one, you have a little hammer, right? And you hit the one mole and then it pops up somewhere else. So, we've got all kinds of stories of that where someone, goes and changes the bypass capacitor or something, and they fix one oscillation and then another one, pops up somewhere else. So there's all kinds of, trying to design, especially like I said, when you get to high frequency circuits, trying to design something stable, it is just a nightmare, because you never can be sure. That's the thing with circuit simulation, and that's why I've been pushing this idea of designing the circuit to be stable, because if you don't design the circuit to be stable, you just don't know. You have no idea. And then when these harder specs start kicking in, like pulling viswar, it makes it very difficult. So, and there's nothing worse as a designer, an engineer, trying to develop a circuit when you put it on the bench and you expect it to be an amplifier, and then all of a sudden it's like, it starts oscillating, and you don't know what's going on, right? It's like you just feel like a failure as an engineer. You go, this thing is supposed to be an amplifier, and it's not. It's doing all this, and you have no idea what it's doing. So that's a really sinking feeling as a hardware developer. And so yeah, it's very easy to design an oscillator that's at the wrong, or doing the wrong thing. If you're trying to design an amplifier, it's very easy to design an oscillator, it turns out. And even if you're trying to design an oscillator, it's easy to make an oscillator at the wrong frequency. It's not such a hard thing to do.
So one thing that's come up in a few other interviews we've done is 5G has really caused people to reshape and rethink how they go about their design and test problems. Has that rippled into the simulation world at all?
Yeah, absolutely. The waveforms for 5G are just so much more complex, and just like making a measurement, on the measurement side, we've had to come up with some innovative ways to simplify that process, make faster measurements, still be, have them be accurate. In simulation, we have the same problem. If we have this really complex waveform, like demodulating it is a long process. Sometimes we need to run an IQ signal through that. So one technique in particular, one example of that anyway, is this technique called modulation distortion, or in simulation we call it distortion EVM, error vector magnitude. And then it's actually a measurement technique that we're able to apply also to the simulation space. And essentially what you do, if you think about a spectrum, is you have a signal coming out in the spectrum, and then you have these sidebands, the noise. And we're able to actually mathematically, on the measurement side, we're able to mathematically separate the individual, original carrier signal from the distortion terms. And in doing that, we can compute EVM without having to do a modulated signal. Well, we can use the exact same technique in the simulator, and we can save tons of time. You can all of a sudden start optimizing this thing. Instead of needing to sort of virtually demodulate your signal in the simulator, now you can just run it through a function, this distortion EVM function, and you can really quickly calculate error vector magnitude. And that opens up this whole world of being able to optimize, drive down the error vector magnitude in your simulation. And we're seeing that in a lot of areas, particularly driven by 5G. So
that makes sense. Yeah. It seems like simulation would be super handy there. As we are wrapping up on time, are there any tips or advice you have for people who either have been thinking about simulation or just starting to get into it, or even any pro tips that a lot of the experts miss as they're going through this?
Yeah, well, I mean, with the simulation stuff, it's really easy to get a trial license. So if you're a university student, you can basically pick up a license pretty much for free. And there's also ways to get trial licenses of the simulation. There's a lot of great YouTube videos out there that, if you're just getting started for the first time, you can go watch these videos and they'll get you up to speed really, really quickly on how the circuit simulation works. The thing that I've always, and back to sort of what I've told people, the pro tip is, only model what's important. And it's your job to figure out what that is. So a lot of times I see people just overdo it on the modeling, and it bogs everything down. But if you can figure out what's important in your circuit to model, then you're going to have the fastest possible simulation with the most accuracy that you can possibly achieve. So that's my pro tip of the day.
That's good advice. And Matt's being humble because he has a ton of hands-on videos on the ESOF YouTube channel, EESOF, Keysight ESOF. He's all over that channel. His videos have tens or even hundreds of thousands of views. So go check those out if you're interested. And we're also adapting some of those into Keysight University courses. So there's a lot of information out there if you want to get your hands dirty. Matt, thank you so much for your time and your expertise.
Sure. No, thank you, Daniel. It's been really a fun conversation.
So what an awesome interview with Matt. Honored to have him. I know we saw some questions rolling in that we will do Q&A in a moment. But first, we have some winners to announce. We have our drawing winners from the Keysight University Live Sweepstakes, and we have the Smart Bench Challenge winner, our first week's winner. For the Smart Bench Challenge, you can see the link at the bottom of the page. You basically have to submit an entry telling us why you think you should win test gear, and we will be announcing a new winner each week, every week for this event. The last entry is, I think, April 20th is the last chance to get your entry in for that last selection on April 27th. So the winner of that, if we can pop up the screen, is Mark Hughes. Congratulations, Mark. You can see his entry here. He had a write-up of why he thought he should win, and a video. Is a great little video. He's done some stuff. He does Teach Me PCB course. He's also creating some other content. So some really great educational stuff coming from Mark. So go check out that entry. We'll put a link in chat. We'll put a link over on the Smart Bench Challenge page as well, so you can find that there. So congratulations to Mark. You have won a full set of Smart Bench Essentials setups. That's a scope, a function generator, a DMM, and a power supply. Today's winners also winning their choice of one of those 4 Smart Bench Essentials. We announced 4 already over on the video down low, but we'll announce them again here as well. Logan Betts, Philip Kraus, Patrick Moore, Louis Pesco, and Leander Beckler. Congratulations to those winners. We are also every day giving away a first prize winner. You get one of the fancy 3000 T-series oscilloscopes, a function generator, DMM, your choice of a list of things is Angel Aguilar. Congratulations, Angel probably. And we have 3 winners every day who win a U1282A handheld DMM. Those winners are Stephen Reed, William Bello, and Bradley Leonard. Congratulations to our winners. We are drawing new prize winners every week. We will announce those each Tuesday in the live stream here at 10 a.m. Mountain Time. We'll also be doing chat and hanging out with you guys for a bit like we've been doing. So I'm going to pull up the chat window. The team has also been monitoring some of these chats and sending me questions. A question we keep getting is, where do I get my T-shirts? The internet. There's a bunch of T-shirt sites, and you just kind of go searching for geeky T-shirts, and if you find one you like, you get it. That's where I get my T-shirts. A couple questions about simulation. So we had some really cool questions coming in. One was like, could you emulate an entire SoC or a system on a chip like the Apple M1? Yeah, with these simulation tools, you can. They're using them, especially for like 5G chipsets, like Matt talked about. RF is where we see a lot of these simulations, but you can also do. If you look up Keysight Pathwave test and simulation software, we have a whole bunch of more than I could go into, more than I can even like wrap my head around. A ton of simulation stuff out there. You can do thermals, you can do oscillations, like Matt was talking about, where he sent those videos over where it was like oscillations at high frequencies, oscillations at low frequencies. You can do thermal characteristics, all sorts of different things. Since we're doing live chat, we're also toying around with doing Twitch. So if you want to see us on Twitch, let us know in the comments. I actually set up a channel over the weekend. If you go to Keysight Labs on Twitch, you can see us there. We're still figuring out what we're going to do there, but if that's something you want to see from us, let us know. We're really interested. We've had a ton of fun doing these Q&A, and I think you've had a ton of fun as well, so we'd love to have a spot for more regular streaming to hang out while we work on things like this. So the RC car was a lot of hands-on stuff to make this actually work. You know, we obviously pulled apart the remote and everything. You can leave the camera there. Doing some streaming, some Q&A, some builds as we're actually going through and testing this sort of thing. So if that's something you're interested in and you're on Twitch, let us know in the comments. Let me know on Twitter, and go check out our channel that we've set up, Keysight Labs on Twitch. We're going to play with it. I'm sure we're going to stream a little bit and just kind of see how it goes from there. I haven't done Twitch much myself, but we stream, so how hard could it be? And it'd be a ton of fun to hang out and hear what you're working on and have some of this less formal streaming. The YouTube videos are very highly edited, and you don't get to see a lot of the behind the scenes. So this would be a chance to kind of see how it all works and get some time with test gear and see it actually in action that you wouldn't normally see in a video that we release. So if you're interested in Twitch, Keysight Labs, go check it out. You can also check out the Keysight Labs YouTube channel. We are over 95,000 subscribers. If we hit 100,000 subscribers during this event, we will give away extra test gear, some extra scopes. So tell your friends, tell your engineering friends, share these videos, share this event, and we're really hoping to get to 100K before the end of April, and we'll give away some extra test gear if we do. Other questions that came in during chat. What's the most interesting thing that you can suggest for a mechanical engineer? That's a really good question. We have a couple of mechanical engineers on site here. They do a lot of I joke that they only do thermal management, but there's a lot that goes into making sure that these are sturdy. They can handle being shipped, being schlepped around on the bench. We even have drop tables and stuff. I think we have some videos of a UXR on a shake table that may come out at some point. We'll see. What they've told me that they find most interesting is I've gotten a lot of good information about. Someone followed us on Twitch. Hey, look at that. Is that they really like the Double E's Talk Tech podcast, EES Talk Tech. It's a lot of high-level overviews into different technologies, kind of like we've been doing here on this live stream with these interviews every day. We're probably going to put some of these over on the podcast as well. We may have some extended cuts of some of these to flesh out a little more that we thought would fit for a podcast, but maybe not for the video. So that's a good place to start, is what is interesting to you? And instead of trying to crack open a textbook and figure out what's going on, the podcasts are great. We have over 50 episodes. Our blogs are also pretty good, so you can poke around and see what's over there. Some are more technical and some are more topical, so you can check that out. And of course, the Keysight Labs YouTube channel, we put a lot of work into that to make sure it's both accessible and people can learn technical things. So Like in the RC car video, we talked about voltage limits. There's a whole bunch of other things that we did with the function generator to make sure it worked, like the trigger button. So I had the big red button that you could press to do a single shot burst waveform. Things like that, we try to make that both accessible for people who aren't as experienced with this equipment and this type of testing, but also fun and educational for people who are doing that stuff. So that would be my recommendation. There's also there's a whole community on YouTube of great YouTubers that are doing all sorts of varied levels of technical depth. So like Great Scott is one of my favorites, and Electro Boom, of course. Andreas Spies, the Signal Path, a couple other, EEV blog, Dave Jones over there. He actually just did a teardown of the DMM, so you can go check that out. I think he released it last night. It might have been Sunday night. Other questions. How does this true form generator compare to the turbo encabulator? That's a comparison I think you'll just have to see to believe. That's coming next week, so I'm really excited. We have some surprises up our sleeve for that one, so I don't want to ruin that one. Let's see, what else? Any follow-up on the oscilloscope assembly video? I'm not sure what the oscilloscope assembly video is, so you have to be more specific. A couple other questions. What program should we use to simulate PCB designs? I want to simulate temperature of IC and noise. So there's a number of things out there. You can check out Pathwave and see if it fits what you need it to do. There's kind of these different types of CAD programs that do functional versus verification. So you have to find a workflow that works out for your system and also your budgets, because some of these ADS CAD programs on the enterprise scale are pretty spendy. I talk with the ASIC designers that sit on the other side of this door and look through their tool chain, and it's pretty complex and it's fairly spendy. We got some questions previous days about RISC-V open source FPGAs. I think that is a great platform. So if you're looking to do like FPGA design, then you can look into the RISC-V stuff. Someone's also done a 0 to ASIC program. So you can go, if you search 0 to ASIC, you can find that. They're doing some really cool stuff about how to actually design your own ASIC. And Google is even opening up some spots in silicon. So you could potentially design your own ASIC and get it fabbed. I think it's for free by Google with this program that they're running. So that is interesting. It's worth checking out. I think if you just Google 0 to ASIC, it'll all be there. That's not a Keysight program, but I love what they're doing over there. Other questions coming in. Could you remark on EMI shielding in Q&A? Yeah, so EMI shielding, we look at the metal backing if you watch like Dave's teardowns, or if you look, I'm trying to think where we've shown shielding. We generally don't disassemble things too much. Because R&D gets, I won't go down that path. But there is some, obviously shielding for EMI. A lot of that is there's two reasons you do shielding. One is so that you don't get noise on your systems. So you'll see even like isolation slots cut into PCBs. You don't want the noise from like your switching power supply or your other lines in your instrument interacting and impacting your measurement. The other reason you do shielding is to make sure you're passing like FCC guidance in the United States or the European and other countries' equivalents of those. So, the Zach. Okay, so they're asking about the Zach Frieden oscilloscope assembly video. Yeah, I wanna get my hands on that, and he's in Colorado now. So I think once vaccinations roll out a little better here in Colorado and things are a little more friendly health-wise, we'll be pulling him in. We're excited. I love that channel. It's a cool channel too. He water-cooled an oscilloscope. He also did some RGB fun. It's a cool video. Go check it out. It was actually one of the most controversial videos we've seen from any creator about Keysight equipment. It also got one of the biggest reactions from I got so many emails from R&D folks and just people all over the world who are like, I saw this video, it was amazing, I loved it. Yeah, so you can go check that one out if you want. Zach Friedman is the YouTube channel. He's doing some really cool builds, very, very skilled maker, doing some really cool stuff. People still want the assembly line stream. Yeah, we walked through an environmental testing setup with the shake table and the drop table. There's like giant walk-in ovens and stuff. So that's what we have some footage of. We will we will put together, I'm getting a thumbs up from the editor, yes, we are going to put together that video. Part of it is a lot of the things that were being tested are proprietary. So we filmed it a while ago, but we have to like make sure we can show everything. But it's a really cool team, really intelligent, some of the smartest folks. They let us borrow the anechoic chamber for the Field Fox video. So we love that team and what they're doing. And they make it so that these things last really, really. That's why we can throw long warranties, multi-year warranties and that sort of thing on these and still bring them in at the price points we're bringing them in on. So a lot of work done by that team to identify potential issues and a lot of math and engineering involved to make sure to take a prototype into actual production and make sure it's functional and usable. So other questions. Make a video about magic smoke that makes electronic things work. Yeah, you basically just don't let the magic smoke out and everything works. That's all you need to know about electronics. It's not true. Let's see what other questions are rolling in. Some questions about MATLAB coming through in chat. That is another good question. There are tons of MATLAB integrations with our equipment, both for analysis and signal generation and creation. So I would encourage you to go figure out what specifically you're trying to do and then look into the MATLAB integrations. But even as Caleb said in chat earlier, there are integrations all over the place with MATLAB because we know that's an essential tool. Our engineers use it as well. So I don't think I have it installed currently. But yeah, definitely integrating with MATLAB is something that we do. Another thing that came up in comments on Dave Jones's DMM teardown that I'll address briefly is he mentioned that the DMM doesn't do trends. With the benchtop software, you can actually plot out trends of measurements over time, and that software is free and included with the Smart Bench Essentials DMM. So go check that out if you're interested. The software does a lot. It does control. It's free. It also, that's how we got this to work, is we took signals from our oscilloscope and we piped them in from the oscilloscope and put them onto the function generator using BenchLink Waveform. Let's see if I say it right. BenchLink Waveform Builder Pro software. It's included with the function generators. You get access to the Pro software, and it's like a $300 piece of software. So you almost pay off the function generator in software. It has tons of capabilities where you can draw waveforms with your mouth. You can, or not with your mouse, not your mouth. Well, that would be a funny video. Picturing how that would work in my mind right now. You can draw waveforms with your mouse. You can do multi-channel ARBs. You can create sequences and steps and then chain them together. So that was plan B for this, is if it didn't work, we were going to kind of cheat it behind the scenes a little bit and create some sequences and then build the obstacle course so that the car could get through it. But it actually ended up working, so that was really exciting. We don't cheat in our videos. We just make it work. There's a lot of agony for that video. So other questions in chat. Let's see what's coming in. Lots of different students. We love to see students. That's fantastic. Mechatronics degree. That's some pretty cool stuff. I wish I had done more in mechatronics, but I'm learning, especially with something like this where you're driving motors. I'm wanting to take the electronic load and hook it up to this and do some battery testing. So if that's a video you want to see, let me know. That's definitely something that we could do with this and see what sort of battery life we get under different conditions. Would be really, really interesting. Let's see, Caleb Begley, Fun and Tech in chat is saying, one word of warning, before doing temperature corner simulation using SPICE tools, make sure your SPICE models are designed for the temperature range you're looking at. So that's a really good caveat. Yeah, there was a couple questions about how does manufacturing tolerances and component tolerances, how do they affect your simulations? And one thing we talked about with Matt, and we'll talk more in a future episode with David Root about parameters is, someone's trying to open the door into the studio. What they're talking about component parameters is your simulation tools have to account for those tolerances. So usually there's a setting somewhere and you can change it, but that is something to be aware of. One reason that simulations aren't going to match or could not match real life is if you had poor tolerance settings or manufacturing settings in your simulation tools. So that's a really big one. People are still asking about the factory tour. Someone wants to know where to buy the scope opener. We put a bottle opener on the side of an oscilloscope. That's a video over on our Keysight Labs channel. You can go check that one out. Unfortunately, it is not yet for sale. I've been bugging them to make that post-purchase upgrade, but I don't think that's going to happen. A couple more questions, and then we're going to wrap it up. Thank you all for being here and participating. We love it. You can also get extra entries if you refer more people. So make sure you tell folks that you know. Oh, we got a response from Matt Ozales. Oh, that was a good question. Someone asked about the Smith tubes, the 3D Smith charts. The question was, but a line shape on a Smith chart is already about LRC components, so inductive, reactive, and capacitive components. On frequency, I don't understand why adding another dimension for frequency is necessary. And Matt says, by adding another dimension for frequency, you can show the individual trajectories of each component at every frequency. Normally in 2D, this would only be done at a single frequency. Now we can extend that out to see how it changes as the frequency changes. So yeah, there you go. Thank you, Matt, for that answer, and great question. That is an excellent question. Also, a couple people asking about Twitch again. Keysight Labs on Twitch. I don't have a link. We just set up the channel this weekend, but if that's something you're interested in, go follow it. Let us know in chat. Let me know on Twitter at Daniel Bogdanoff, and we'll do that. I'd love to try that out because this has been awesome. People are asking for mugs. Yes, I know. Mugs are really difficult to ship out. So we're talking about it. Maybe hit that get special access, and we'll maybe ship some of these out. We also have some of these cool lab notebooks. If you are lucky enough to be here ahead of time before the stream actually starts, there's a countdown timer, and you can see we have some cool lab notebooks that we are very much considering giving away to some folks that are part of this event, and I promised to send some out earlier, so that's happening as well. That's my least favorite picture. Stonehenge with RCal or eCal. It's an RCal for a signal analyzer. So we are doing some of that, so make sure to hit the Get Exclusive Access button. You only have to hit it once. You don't have to hit it every day. But that is how you can make sure you get stuck, or how you get updates on that, not stuck. Let's see, other questions, and then we're going to call it a yes. Someone says these are much easier to ship than mugs. For a number of, there's like export restrictions on ceramics and stuff. It's same with t-shirts. It's really, really tricky. One more question. Let's see. Let's make it a good one. Someone from UCCS Physics. Hey, they want to talk about collabs. Talk to your local Keysight contact. We're just down the road. So, yeah, lots of questions about ARBs. Let's see. I also wanted to look at a couple of the comments from the video. People on YouTube had left some comments. A lot of people are talking about how they thought their function generator was good enough until they saw this. The question was, can I basically create any waveform? And yeah, with the function generator ARB, there's a frequency limit. So the frequency cap on your function generator, I think this one's 120 megahertz. Yeah, we're not going to pull the camera over to that one. But we have 120 megahertz dual channel ARB. This one I believe is 20 megahertz. So that's the main cap that you have on your function generator. You can create kind of anything you want. You can pull scope traces. You can draw them. You can create test sequences with phase offsets and all sorts of DC offsets. And there's all kinds of fun stuff there that you can do with them. We're going to call it a day. We'll be back next Tuesday. So make sure to set your calendar for 10 a.m. Mountain Time. I believe that's -6 UTC off the top of my head. I'd have to double check. You should double check if you're putting it in your calendar. And we will see you back. We have another fun week planned for you. We'll talk about the turbo encabulator and a whole nother interview, another stream, and more QA. Thanks for watching. I'm Daniel Bogdanoff, and I'll see you next time.